The first lesson of this unit is on the mole. And no, not that mole, the Avogadro's number mole. We're going to learn what is Avogadro's number, how do we use it, and you're going to understand more about this number than you ever thought possible. But before we begin with Avogadro's number, let's do a little pre-unit question. Look at this molecule here. This is the acetaminophen molecule again. Think about, where do these atoms come from? Not where does the molecule come from, that's made in a factory. Where does the nitrogen come from? Where do the carbons come from? Where do the hydrogens come from? What do you know about the origins of atoms? If you don't know anything, maybe make a guess about where you think these atoms could come from. By the end of this unit, you're going to really know in a very specific detail where these atoms come from. But for now, put your response in your notebook, and then we're going to come back to this at the end of the unit. Let's start this unit by looking at the structure of an atom. Here is the simplest atom that we have. We have a hydrogen atom. Hydrogen atoms contain a proton, and they also usually contain one electron. That electron orbits the proton. And the area where we find the electron is the shell. Here's another atom for reference. We have a helium atom. What's the difference between the helium atom and the hydrogen atom? Well, the helium atom, of course, has two protons, and it has two electrons in this case. It also has a shell. So what is it exactly that makes the atom on the left a hydrogen and the atom on the right a helium? Is it the number of protons, the number of electrons, the number of shells? What is it? The only thing that defines what an atom or an element is the number of protons, not the number of electrons. A lot of people think that it's really just the number of protons. What if I add neutrons to these atoms? What if I put one neutron in the helium atom or a second neutron in the helium atom? Does that change what atom or element it is? No, it's still a helium atom. Something that we're going to see a lot in this unit is atoms with different numbers of neutrons. This becomes a very interesting topic. Now, I said before that the number of electrons does not define what kind of an atom you have. You could take this helium and remove an electron. Is that still a helium atom? Yes, it is. It's just a charged form of helium, but it's still a helium atom. So from this point forward, you're never going to forget that a hydrogen has one proton. That's what defines a hydrogen. And a helium has two protons. That's what defines a helium. We can have different numbers of electrons, different numbers of neutrons, but what matters is the number of protons. Now you're going to see this over and over again, so it's almost not even worth me saying this, but the protons have a positive charge, which is why I put a positive sign on the protons. Electrons have a negative charge, which is why I have the negative sign on the electrons. In neutral atoms, we have a balance of protons and electrons, but there's no reason we can't have a different number of protons and electrons. But in neutral atoms, there has to be a balance of positive protons and negative electrons. So that's all great, but what's the connection to the periodic table? Well, the connection to the periodic table is in those atomic numbers that you find at the top of every element symbol. Hydrogen is element number 1, helium is element number 2. It's not just because we think hydrogen is number 1 and helium is number 2. It's because hydrogen has one proton. Heliums have two protons. So what you can think of when you look at these element symbols, whatever number is above the element symbol, that's the number of protons. Let's do a little bit of practice now. What element is this? Well, let's count up the protons in the nucleus. We have 1, 2, 3, 4, 5, 6. This must be element number 6. It's a little tricky because I've put a weird number of electrons. I've only given you 2 electrons, and that's fine. You can have an element with the wrong number of electrons compared to its protons. That's okay. It's a charged form of that element. But what element is this? Well, it's carbon because it has 6 protons, and carbon is number 6. It has 6 protons. So a carbon atom is synonymous with the number 6 because it has 6 protons. Now, we typically see carbon in its neutral form with 4 additional electrons for a total of 6 electrons. Those extra 4 electrons live in another shell, and that extra shell is farther away from the nucleus, and it has certain behaviors and properties which we study in a different unit. But for now, just remember that carbon is associated with number 6, 6 protons, and if we want a neutral carbon, 6 electrons. We also very often have 6 neutrons in the nucleus. And of course, the nucleus is where we have all the protons and neutrons. Protons don't fly around the atom, and neither do neutrons. Protons and neutrons live in the nucleus, and electrons live around the nucleus. Let's go through the first several elements and see what's the typical number of neutrons that each of these elements have. We already know how many protons they have because the number of protons is the same as their atomic number, right? So that's a kind of trivial, easy thing to learn, the number of protons. But what are the number of neutrons? That's a little bit more tricky. Let's start off with element number 1, hydrogen. Hydrogen typically has 0 neutrons. It's the only atom that is stable with 0 neutrons. So you'll never see atoms without neutrons except for hydrogen. What about helium? Helium's number 2, 2 protons and typically 2 neutrons. 2 neutrons is typically what we expect for a helium. Carbon we already looked at. Carbon is synonymous with the number 6, 6 protons, usually 6 neutrons, usually 6 electrons for a neutral carbon. That is our story for carbon. All right, what's the story with nitrogen? Well, nitrogen is element number 7, and it has 7 protons, and typically 7 neutrons also. It's the same. How about oxygen? Oxygen has 8 protons, and you might guess that it usually has 8 neutrons, right? And then continuing the pattern, fluorine has 9 protons, and how many neutrons? 10. This does not follow the pattern. We do not find fluorines with 9 protons and 9 neutrons. It's 9 protons and 10 neutrons. So not all atoms have the same number of protons and neutrons. We knew that from hydrogen going into this, but other elements too do not have to have, and some can't have, an equal number of protons and neutrons. So we're going to start to answer why that is in this unit. If we were to take away a neutron so that we only had 9 neutrons for our fluorine, this would be a radioactive element, an unstable element, and this kind of an element does not last forever, and it usually gives off radiation. So these kinds of elements are problematic, and we're going to learn more about them later in the unit. I wanted to give you a little help and some mnemonic devices so that you could remember how many protons are in the first few elements of the periodic table. For the hydrogen, we have one letter H, and we can imagine a 1 on one of those bars of the H. Helium is also with an H, but it has 2 letters, so 2 protons. For the carbon, we have a C that also looks like a 6, so we can remember that carbons have 6 protons. What about for the nitrogen? Well, if you turn the N on its side, you see the 7. Nitrogens have 7 protons. Oxygen's symbol is O, so if we put 2 O's on one another, we have an 8. And what about fluorine? Well, if we flip the F around, it looks kind of like a 9. So here are some mnemonic devices. If these help you out, great. If you don't need it, it's fine also. Now coming back to this problem with fluorine, why is it that fluorine is not allowed to have the same number of protons and neutrons? Why are there 10 neutrons but 9 protons? Well, part of the reason is the idea of nuclear magic numbers. So what are nuclear magic numbers? This is probably something that you haven't heard of before. There are 7 magic numbers of protons and neutrons on the periodic table. We have 2, 8, 20, 28, 50, 82, and 126. So what are these magic numbers? Well, they are very stable numbers of either protons or neutrons. For example, oxygen has 8 protons. That means that it has a magic number of protons. If an oxygen has 8 neutrons, it also has a magic number of neutrons. What about helium? Well, helium has 2 protons and 2 neutrons, so helium is also doubly magic. It has 2 protons and 2 neutrons. It has a magic number of both protons and neutrons. What about nickel? Well, all nickel atoms have 28 protons, so they have a magic number of protons. The nuclear magic numbers are simply very stable or very favorable numbers of either protons or neutrons or both. So let's look at fluorine. Fluorine has 9 protons and 10 neutrons. If I tried to make a fluorine with 9 neutrons, we have a little bit of a problem. The problem with this fluorine is that it has the number 9 twice. And what is a magic number? 8. 8 is very, very stable, very, very favorable, very desirable, but we have 9 of both. If you're a fluorine and you have 9 protons and 9 neutrons and you are right next to this magic number 8, you're looking over at the oxygen saying, wow, you have 8 protons and 8 neutrons. That's great. I have 9 and 9. That is sort of a problem for this fluorine. So what does the fluorine do to try to become more stable, to try to get those magic numbers? Well, it can't change both at the same time, but what it can do is it can, in a radioactive decay, lose one of the protons. So that proton that you saw wiggle there is the extra proton. It's the unwanted proton. If that proton was to somehow, let's say, change into a neutron, then what is our situation? Our situation is that we now have an oxygen, first of all, because one of our protons changed into a neutron. And now we have also 10 neutrons because the number of neutrons went up. Our neutron count went up. What's great about this situation? Well, now we have 8 protons. Isn't 8 one of the magic numbers? So we went from a situation where we have 2 numbers, the 9s, which are so close to the magic numbers, and now we've actually gotten one of those magic numbers. We have 8 protons. That sort of a situation is part of what goes into knowing whether an element is stable or whether it's radioactive, whether or not the element will last forever or whether it will decay into another element. The magic numbers can sometimes guide us and help us understand why certain forms of atoms are possible and others are not possible. So we're going to explore this a lot in this lesson. Why are we looking at a bunch of Skittles right now? I'm going to use Skittles as an approximation for a gram. Skittles weigh about a gram. What is a gram? Well, it's a unit of mass. When something weighs a gram, it's about the size of a Skittle. So when you see a gram, I want you to visualize a Skittle. How many grams are I looking at right now? Well, if you count up the Skittles, 1, 2, 3, 4, 5, it looks like there's about 15 Skittles. So how many grams is this picture of? It's of 15 grams. I want you to get very comfortable with the idea of a gram. I don't want grams to be something that you don't know what a gram is. A gram is like a Skittle. So let's use a balance and show you how you would actually weigh out a Skittle. Here's a balance that is a very fancy balance that you'd find in a chemistry lab. It's an analytical balance, and it has this special glass chamber over the balance. So what's that about? You would basically open up the windows on either side, put your chemical in, and then close the window. The point of this is to prevent any gusts of wind or breezes to affect the measurement of your chemical that you're weighing out. But here we're going to virtually weigh out a Skittle. Let's just throw a Skittle on this balance. This Skittle should weigh 1 gram, 1.000 grams. That's what it says on the balance. A Skittle weighs about a gram. What if you had 1,000 Skittles? How much should that weigh? Well, I'm not going to show that to you, but that should weigh 1,000 grams. What if I had 1,000,000 Skittles? That should weigh 1,000,000 grams. You get the idea, right? 1,000,000,000 Skittles should weigh 1,000,000,000 grams, and so on and so forth. It becomes difficult to visualize what a sextillion of Skittles would be. Luckily, we don't have to weigh out that many Skittles, but we do have to weigh out sextillions of atoms. So let me talk to you about what that means. If I were to, instead of weighing out 1 gram of Skittles, which is 1 Skittle, and I wanted to weigh out 1 gram of hydrogen, what would that look like? Well, it's going to be a lot of hydrogen atoms. The question is, how many hydrogen atoms is that? How many hydrogen atoms is a gram of hydrogen? This is a really, really important question. You may want to write this down just to focus yourself. Write down how many atoms are in 1 gram of hydrogen. What could that look like? Well, it's in the sextillions, all right? I have this little key on the top here. It says gray circle equals 100 sextillion hydrogen atoms. So I'm going to put 100 sextillion hydrogen atoms on the balance. And then I'm going to put another 100 sextillion hydrogen atoms on the balance. And another 100 sextillion hydrogen atoms. And I'm going to keep doing that until I get to 1 gram. It turns out that 6 of these little gray circles, which is equivalent to 600 sextillion hydrogen atoms, that weighs pretty much 1 gram. So whereas before we had a Skittle that weighed a gram, now we have 600 sextillion hydrogen atoms that weighs a gram. You may want to write this down. 600 sextillion hydrogen atoms weighs about 1 gram. This turns out to be an extremely important fact in understanding chemistry and quantifying or counting things or measuring things in chemistry. It's so important that we've given this number, 600 sextillion, a special name, and that name is a mole. 600 sextillion of something, whether it's atoms or molecules or anything else, is called a mole. So what you're seeing on this balance is a mole of hydrogen. That's how a chemist would talk about it. Let's try another question to help you understand. I want to now weigh out not 600 sextillion, but 1,200 sextillion hydrogen atoms. Not 600, but 1,200. What's the relationship there? I'm first going to add 600 sextillion hydrogen atoms. Then I'm going to add another 600 sextillion hydrogen atoms. Think about how much that should weigh. Think about how much the first 600 sextillion weighs, and then think about how much it is if I add another 600 sextillion. Well, you guessed it. It should weigh 2 grams. We've weighed out twice as many hydrogen atoms, so it should weigh twice as much, not 1 gram, but 2 grams. So 1,200 sextillion hydrogen atoms weighs about 2 grams. We know that 600 sextillion is a mole, so how much is 1,200 sextillion? That's 2 moles. So you're looking at 2 moles of hydrogen weighs about 2 grams. 2 moles of hydrogen is 2 grams. Now we're going to weigh out 2,400 sextillion hydrogen atoms. Not 2,400 sextillion grams, because that would be a lot of Skittles, right? Just 2,400 sextillion hydrogen atoms. So let's put down our first mole, our second mole, our third mole, and our fourth mole. Remember that 1 mole weighs a gram, so 4 moles should just weigh 4 grams. 1,200 sextillion hydrogen atoms weighs about 4 grams. That's 4 moles. Let's compare that to the 1 mole situation. Remember, 1 mole is 6 of those little circles, 600 sextillion hydrogen atoms. Now I have 24 little gray circles, so that's 2,400 sextillion hydrogen atoms. The balance on the right has 1 mole of hydrogen, or 1 gram. The balance on the left has 4 moles of hydrogen, or 4 grams. How many moles of hydrogen is 1,000 grams of hydrogen? If I had 1,000 grams and put it on this balance, how many hydrogen atoms would it be? Well, if 4 grams was 4 moles, 1,000 grams should be 1,000 moles. What if we had 1,000,000 moles of hydrogen? How much should that weigh? 1,000,000 grams. Because 1 mole of hydrogen weighs a gram. So however many moles we have, it's the same number of grams. And that's for hydrogen atoms. Let's move up the periodic table, and we're going to now deal with helium. Here's a question. How much does 600 sextillion helium atoms weigh? Now, why did I do 600 sextillion? Well, that's a mole, right? So I'm asking the question, how much does a mole of helium atoms weigh? Well, first we have to look at what a helium atom is. It has 2 protons and 2 neutrons. Protons and neutrons weigh almost the same. And a helium atom looks like it's about 4 times as many things as a hydrogen atom, right? Because a hydrogen atom has 1 proton in the nucleus, and here we have 4 particles. So let's weigh this out and see what happens. We're going to weigh something out that weighs 4 times as much as a hydrogen and see how much it weighs. Oh, it looks like it weighs 4 grams. Does that make sense? A helium weighs 4 times as much as a hydrogen. So if I weigh out a mole of them, that mole should weigh 4 times as much as a mole of hydrogen. So what we're looking at is 600 sextillion helium atoms, which weighs about 4 grams. Even though this is heavier, it's still a mole because we have 600 sextillion of that particular atom. Let's compare that to the example that we did before, where we weighed out 4 moles of hydrogen atoms. 4 moles of hydrogen atoms has 24 particles in it, right? It has 6 plus 6 plus 6 plus 6. That's 24. Look at the mole of helium. The helium has 4 plus 4 plus 4 plus 4 plus 4 plus 4. That's 4 times 6, which is 24. So there's 24 either protons or neutrons on the left side and 24 protons and neutrons on the right side. That's why these 2 things weigh the same. So isn't it interesting that a mole of helium weighs 4 grams, but 4 moles of hydrogen also weighs 4 grams? You may be starting to get a little bit confused right now. That is very normal. Everyone's confused the first time they learn moles. But by the time this unit is over, you are definitely going to understand moles. And probably by the time this lesson's over, you're going to definitely understand moles. So let's keep going. Let's look at some more examples, and we'll get more familiar with the idea of a mole. Let's try carbon. How much does 600 sextillion carbon atoms weigh? Again, I chose that number because that's the mole number. I'm going to use my key here again. That symbol represents 100 sextillion carbon atoms. Let's add 1, 2, 300 sextillion, 4, 5, 600 sextillion carbon atoms. How much should that weigh? Well, let's look at what a carbon atom actually is. It's 6 protons and 6 neutrons. That's how many times heavier than a hydrogen atom? 6 plus 6 is 12, right? So a carbon atom is 12 times bigger than a hydrogen atom. Do you think this should weigh the same as a hydrogen mole? Should it weigh the same as a helium mole? What do you think? It looks like bigger, right? It looks more. So this should definitely weigh more than a mole of hydrogen, which is 1. It should definitely weigh more than a mole of helium, which is 4. How much is it? Well, the nucleus has 12 particles inside. So this is going to weigh 12 grams. That's all it is. Once you realize that the mass of a mole is the same as counting the protons and neutrons, you will understand this topic. 600 sextillion carbon atoms weighs about 12 grams. That's a mole of carbon. Compare that to the hydrogen. That's a much smaller mass, isn't it? A mole of hydrogen only weighs 1 gram because these are little tiny particles. A mole of carbon weighs a lot more, weighs 12 times more because the particles of a carbon, the carbon atoms, are 12 times as big. They have 6 protons and 6 neutrons. 12 grams of carbon is a mole. Only 1 gram of hydrogen is a mole. Let's do some more examples, and you will definitely get this in a few minutes. How about nitrogen? How big is a nitrogen? Well, it has 7 protons and 7 neutrons, remember? So that's 14 total. How much bigger is a nitrogen atom compared to a hydrogen atom? 14 times as big, right? Let's add our mole of nitrogens and see what it weighs. We're going to add 600 sextillion nitrogen atoms. How much should that weigh? Well, it's definitely not going to weigh 1 gram. It's definitely not going to weigh 4 grams. It can't weigh 12 grams. It weighs 14 grams. A mole of nitrogen is 14 grams because the atoms are 14 times the size of a hydrogen. Let's compare it again. The hydrogen nucleus is only 1 particle, so if we weigh out a mole of it, it weighs 1 gram. A mole of nitrogen is 4 times heavier, weighs 14 grams. I think this is starting to make sense for you. Let's go on and we'll do a few more of these. 600 sextillion nitrogen atoms weighs 14 grams. A mole of nitrogen weighs 14 grams. How about the oxygen example? What is an oxygen nucleus made of? 8 protons and 8 neutrons, right? Let's add a mole of these guys. 1, 2, 3, 4, 5, 600 sextillion atoms. That's a mole. How much should this weigh? Well, there's 8 protons and 8 neutrons, remember? 8 plus 8 is 16. So this weighs 16 grams. 600 sextillion oxygen atoms, which is a mole, weighs 16 grams. And if we compare that to the mole of hydrogen, definitely looks 16 times bigger. And finally, for our friend fluorine. Remember, fluorine is not 9 plus 9, it's 9 plus 10, right? So the size of a fluorine nucleus is 19 particles. Let's add a mole of these and see how much it weighs. We're going to add 600 sextillion atoms, or 100 sextillion times 6. How much should that weigh? It weighs 19 grams. Doesn't that make sense? Because the mass of a fluorine is 19 times bigger than a fluorine's mass. We have a mole of fluorine, which is 19 times bigger than a mole of hydrogen. So by now you've heard me say this number, 600 sextillion, many times. This is called the mole. It's also called Avogadro's number. It's the same thing. Here's our portrait of Amedeo Avogadro. That's his portrait right there. The typical number that chemists will quote for Avogadro's number is actually 602 sextillion. I've been saying 600 sextillion. I've been rounding it off. I have no problem with students as they learn thinking of the number as 600 sextillion. That extra 2 really doesn't change our calculations very much, and I'd rather you understand intuitively what Avogadro's number is. But I will start to use 602 sextillion more often. The exact number with all of our scientific precision is this number right here. That's the exact Avogadro's number. Typically, we'll see people using scientific notation, 6.02 times 10 to the 23rd. If you're good with scientific notation, you can think of it that way, but I like to say 600 sextillion for beginners. This is also known as a mole, of course. So all these numbers are basically the same thing. Let's look at some examples to help us understand Avogadro's number even more. Here is a list of our favorite atoms. And here's a question. How many atoms are in 1 gram of hydrogen? Well, you saw that a few times, right? That was the 6 little gray circles. That weighed 1 gram. And each little circle represented 100 sextillion, right? So we have Avogadro's number, 602 sextillion atoms. What if we had 4 grams of hydrogen? How many atoms are in 4 grams of hydrogen? That's also Avogadro's number, 602 sextillion. What if I weighed out 12 grams of carbon? Well, because carbon weighs 12 times as much as hydrogen, a mole of it must also weigh 12 times as much. So 12 grams of carbon is a mole. What about 14 grams of nitrogen? How many atoms of nitrogen is that? Well, that's also a mole. What about 16 grams of oxygen? Well, 16 grams of oxygen is 16 times more than the 1 gram of the mole of hydrogen, right? So this is also a mole of oxygen. It's 602 sextillion atoms of oxygen. And then finally, what if I weighed out 19 grams of fluorine? How many atoms of fluorine is that? Well, that's 602 sextillion, Avogadro's number, 1 mole of fluorine. Again, the first time people learn this, they are sometimes very confused. If you maybe watch this video again, come back to it later, watch the next video, these concepts will start to get more solid for you, and you will be able to understand this. Trust me, everyone goes through the same trouble with Avogadro's number. It has sort of a notoriety or an infamy of being kind of difficult, but I hope that all these visualizations are helping you understand what Avogadro's number is faster than normal. How many grams is 1 mole of hydrogen? 1 gram. How many grams is a mole of helium? 4 grams, right? Because a mole of helium must weigh 4 times more than a mole of hydrogen. How much is a mole of carbon? Well, it's 12. How much is a mole of nitrogen? 14. How much is a mole of oxygen? Think about it. 16 grams. And how many grams is a mole of fluorine? 19 grams. One thing that you'll notice is that whenever I ask a question on these slides, the answer is usually right on the slide. I'm never trying to give you a trick question, and there are usually lots of patterns to follow as well. Here's our final review. What's another name for this very big number, 602 sextillion? That's a mole. If you had a mole of something, how many would you have? 602 sextillion. Or you can say 600 sextillion, that's also fine. Which weighs more, a mole of hydrogen or carbon? That should be getting easier for you to remember. A mole of carbon should weigh 12 times as much because there's 12 times as much stuff there, so carbon weighs more. How much more? Obviously 12 times as much. Which weighs more, a mole of carbon or 12 moles of hydrogen? Well, each of those circles represents a mole of hydrogen in this case. 12 moles of hydrogen weighs the same as 1 mole of carbon because it's basically the same amount of things. It's the same amount of protons and or neutrons. The big realization here is that a mole of something weighs a different amount depending on what it is. A mole of hydrogen weighs a different amount from a mole of carbon. We have another final test here. Pause the video and try to answer some of these questions. I want you to discuss neon in terms of Avogadro's number. Now, what is a neon? Neon's element number 10. Most neons have 10 protons and 10 neutrons. So think about how much that would weigh. What would a mole look like? Pause the video and try to answer these questions, and we will come back and answer them. All right, the first question. How many atoms make up a mole of neon? Well, a mole of anything is 602 sextillion, right? It doesn't matter what it is. A mole is a mole. A mole is 602 sextillion. How much does a mole of neon weigh? Well, it says it right there. It weighs 20 grams. Why does it weigh 20 grams? Because there's 10 protons and 10 neutrons. But here's a trickier question. 301 sextillion atoms of neon weighs how much? Why did I do 301? That's not a random number, right? 301 is exactly half of 602. 301 sextillion atoms should be half a mole. If a mole of neon weighs 20 grams, how much does half a mole weigh? 10 grams. So these may or may not be tricky depending on the level of math you have or how old you are, but these are the kind of questions that you have to be aware of in chemistry classes, and understanding this is going to kind of come with time. As we move on, these are going to become much easier. When we look back, you're going to say, oh yeah, of course that's what a mole is. But right now it still might feel a little bit foggy, and like I said, that's very normal as you're learning moles for the first time. Now we've been throwing around this number, 600 sextillion, without really understanding like how big that is, all right? So how big is 600 sextillion? I know that a gram of hydrogen is 600 sextillion atoms, but I can't see that. So how big is 600 sextillion? Think about how many stars 600 sextillion atoms feels like to you. Maybe pause the video for a minute, talk to someone about it. How many stars would you need? What would that look like to have 600 sextillion stars? Think about that for a minute. Well, this picture definitely does not have 600 sextillion stars in it. The universe itself does not have 600 sextillion stars in it. The observable universe has something like 200 sextillion stars in it. What I mean by observable universe, you may know, is that we can only possibly see a certain number of stars and galaxies. The reason is that the universe is expanding away from us, and at those outer reaches, the speed of that expansion is greater than the speed of light. So the light from very distant stars will actually never have enough time to get to us. So there's an observable universe, a physically observable universe that we can only see. It doesn't have to do with how strong our telescopes are. We will never see farther than the observable universe. So while the universe itself may have a mole of stars, the observable universe only has about a third of a mole of stars. Not 600 sextillion, but 200 sextillion. So all the stars and all the galaxies in the universe is not even 1 mole, which is crazy. We would need 2 more universes to just get to 1 mole of stars. What about something smaller, maybe sand? How much sand would be 600 sextillion grains of sand? Think about that for a minute. Is it a beach? Is it 2 beaches? Well, they've done some rough calculations on this. Apparently, all the sand and all the beaches and oceans of the world is only 100 sextillion grains of sand. So you'd need 5 more Earths worth of sand to get to just 1 mole of sand, 600 sextillion grains of sand. So can you have a mole of something? Well, yes, you can have a mole of something. This cube is a cube of graphite. Graphite is basically carbon. How many atoms are in this cube? Well, this cube weighs 12 grams. So if I have 12 grams of carbon, how much carbon is that? Well, remember that a mole of carbon weighs 12 grams. So what you're looking at here is a mole. This cube has a mole of carbon in it. It has 12 grams of carbon, which is also the same as 600 sextillion atoms. So there are more carbon atoms in that cube than there are stars in the universe. We have a mole of carbons in that little cube. 6.02 times 10 to the 23rd atoms in that little cube. What about gases like helium? What does a mole of helium look like? Well, a typical 18-inch Mylar balloon holds about 4 grams of helium, coincidentally. What's so special about 4? Well, there are 2 protons and 2 neutrons in a helium atom. 2 plus 2 is 4. Remember that a mole of helium weighed 4 grams. So what's inside this balloon here? 4 grams of helium, which is the same as 1 mole of helium. So if you get yourself a birthday balloon, not only is this a mole of helium, it's also 4 grams of helium, and it also has a special volume. The volume of a mole of gas is around 22 liters. This is something we can talk about later when we talk about gases, but a mole of a gas takes up about 22 liters of space. So that balloon is something like 22 liters. And of course, because we're dealing with Avogadro's number, we have 600 sextillion atoms of helium in that balloon. So if you ever want a mole of something for your birthday, either ask for a 12-gram carbon cube or a helium balloon. What if you wanted to make your own sample of a mole at home? Well, aluminum is a readily available item in your house. You probably have aluminum foil, and you've probably made an aluminum foil ball before. The question is, how much is a mole of aluminum? Well, aluminum has 13 protons and 14 neutrons. So if we add up 13 plus 14, we get 27. So you would take your aluminum foil and weigh out 27 grams of it on your kitchen balance and make it into a little aluminum foil ball. And what do you have? You have a mole of aluminum. A mole of aluminum is the same as 27 grams of aluminum, which is the same as a mole of anything, which is 600 sextillion of whatever it is, in this case, aluminum atoms. So again, moles of atoms can fit in your hand. Moles of anything else are astronomically huge and basically don't even fit in the universe. Before we end, I want to show you a different version of the periodic table. This is the periodic table that we often see. It has average atomic masses of each element on it. So we've probably seen these numbers before. If you look at, for example, carbon, we see 12.011. For nitrogen, we see 14.007. Those numbers are not the exact numbers that I've been using. There's a very complicated story about why that is. We're going to talk all about these numbers and where they come from in the coming lessons. But for now, I just want you to realize that the numbers that we've been talking about are round numbers that I've been using to help teach you. The really interesting stuff is what goes into these non-round numbers. How do these numbers come about? That's going to be the topic of the next several sections and lessons. So again, when we look at the periodic table, we see that hydrogen weighs not 1 gram per mole, but 1.008 grams per mole. We see that helium weighs 4.0026 grams per mole. We see that carbon weighs more than 12. We see nitrogen weighs more than 14. Oxygen weighs, for some reason, less than 16. That's weird, right? Didn't I say that a mole of oxygen weighs 16 grams, but now it says 15.999? So how does that happen? Same issue for fluorine. Fluorine weighs less than it should. It doesn't weigh 19 grams, like I told you before. It weighs 18.998. So while chemists do usually think of carbon weighing 12 grams per mole, the exact masses are a little different, and we're going to explore where these different masses come from. So if you were to actually weigh out a mole of each of these atoms, you would see almost the number that I've used, but not quite. So that's the topic of the next several sections and lessons. Where do these numbers actually come from? Let's now wrap up this lesson. Let's answer this question. What are some synonyms for a mole? Avogadro's number, 6.02 sextillion, or the same number written out. Those are all the same as a mole. What does a mole of gas look like? If you had a mole of gas like hydrogen or helium, how big would it be? It would be like a balloon. A balloon holds about a mole of gas, which is something like 22 liters. If you had like a metal, what would that look like? Well, it would fit in your hand. Remember the aluminum foil ball fits in your hand? That's what a mole of metal looks like. Now, if you're mathematically minded and want a little research project, you can think of something that is found in very, very large numbers and think about how does that actually compare to a mole? For example, are there a mole of cells in the human body? Are there a mole of ants on the earth? What about the number of kilograms of matter in the sun? Is there a mole of kilograms in the sun? It doesn't seem like we've found anything that fits in the universe that actually is a mole, except for atoms and things. So can I actually get a mole of something somewhere? How do these numbers compare to Avogadro's number? So that's a fun little research project, and you will find certain things that actually there is a mole of, or even more than a mole of, in the universe. But we have to think about what those could be. So that's a fun little research project to get your head around just the scale of the mole. Now that you've completed this section, you can take a much-deserved break. Be sure that you have done the activities in the workbook, and maybe go back and rewatch some of this video to make sure that the idea of a mole is kind of getting through. And if you still feel a little bit confused, you can either review or just kind of keep going on. I think that the more experience you have and the more things that I show you, the easier this will be. So just keep at it, don't give up, and we will see you in the next section.